and it's just like little explosions every time. Like, even underwater, it's amazing. What's up, people? Batmobile turbine engine. You guys need to see that. So, of course, being the replica of the '89 Michael Keaton Batmobile films, needs to have a real turbine or turbo shaft engine as it was portrayed in fiction, but nobody really does that, which is super lame. So, I thought we'd open it up and I'd show you guys how the turbo shaft engine works. Come on over. All right, so I've already gotten the Zeus fasteners out of holding the general hood on. And I'm doing this by myself, which means I have to be clever and try not to ruin my back. Rawr, okay. Setting it down. All right, guys. Well, there's so many misnomers about turbine engines because, frankly, a lot of people don't know much about them. They weren't used much in ground vehicles, unless you have a tank or something that makes a lot of sense. Of course, there were Indy cars back in the 60s who had turbine engines, which is really neat. We'll talk about that a little bit. But primarily, turbine engines of their various natures are used in aviation or typically boats. The reason being is a turbine engine is lightweight. It has less moving parts, it works for a long time, and is really good at making power at a constant rate. Trouble is, some of those things don't work so well for cars that have to speed up and slow down a lot because the turbine engine makes power at a constant rate. So anyway, looking here in the engine bay, and you see what we got going on. I did a video recently on engine swaps in cars, and the biggest two things you run into are basically, do you have the space to do it? And two, what are the logistics with regard to everything you need from cooling to exhaust and all those other things going on, and how are you connecting it to your wheels to drive it? So in this particular custom car, this is a turbo shaft engine. What that means is all turbine engines, or the turbo part of the name, they create thrust. And then the rest of the name and what kind of engine it is just has to do with how they utilize the thrust. So for instance, a turbojet engine, like are in fighter jets, they create a lot of thrust and direct it through a nozzle to propel whatever that engine is connected to through the air, okay? And then an afterburner is they just dump in a whole lot of fuel at the end to make a bigger gaboom to push said vehicle faster. So turbojet engine directs its thrust through a nozzle directly into the atmosphere to move you along. A turbo shaft engine takes all that thrust and internally directs it into another set of, shall we say, fan blades or impeller blades that is connected via a series of shafts or planetary gears to an output shaft. So you're converting the thrust internally into torque, into rotation. And that works really well when you have a turboprop airplane. So it's a turbine engine that's effectively a turbo shaft variant that then spins a propeller. Okay, so turboshaft propeller-driven airplanes, that's how they work. Those are also what's used in a helicopter because it's directing the thrust internally into the blades to spin your rotors and such. Those are also the ones that are used for generators. Turbine engines are oftentimes used for generators. It's something you might use if you even had a hydrostatic-driven something, and also utilized in cars, such as going way back to General Motors prototypes, as well as the Indy cars in the 60s. And as a note, the Indy cars in the 60s did really, really well because at Indianapolis Motor Speedway, you are flat out for a long period of time. So you want to make a lot of power with a lightweight configuration going fast for a long time. The last variant is a ducted fan, or like a, oh crud, I'm losing the name here. What's in commercial airlines? And that's a bit of a combination. You sort of have the turbojet thing going where the exhaust is directed out the back, but basically it's using the shaft rotation to spin a big ducted fan. So it kind of gives you a good balance sort of between a turbojet engine, like in a fighter jet for high speeds, and the difference between a turbo shaft engine that's driving what we call a turboprop. But in the circumstance of a commercial jet airliner, it's effectively got a big ducted fan, so it's more efficient at subsonic speeds and things that aren't going really fast. But it's creating all of its output and power output from the liquid fuel into thrust, with the exception of the heat and any inefficiencies going on with that engine. So this is a turbo shaft engine And the way this custom car works is that thrust is directing internally to a series of blades, which is connected to a planetary gear reduction, which is connected to an output shaft. It's actually connected to a real transmission that, as the driver, you shift, which then is naturally connected to a differential and drives the rear wheels. It does have 4 forward speeds and reverse, and I'll get into how that works. But what I'd first like to do is walk you guys through the engine bay here, and I'm just gonna kind of get all up on this thing so we can dive in. So this particular engine, way back when, was used for a drone helicopter, which is a 2-bladed helicopter in real life, which is similar to the inexpensive drones that a lot of kids get. You have 2 kind of rotating props. They're very stable, and they fly around neat. But this was actually used for a real one. There's surplus and whatnot are around. Some guys have used these in hot rods for fun. I noticed that Tavarish is utilizing a turboshaft engine of a different make and configuration. He was talking about maybe putting that in a Testarossa. He's going to run into a lot of problems when he tries to drive the rear wheels because of spatial considerations, but it's a neat idea. This one works out perfectly for a front engine type car build because the output shaft is on the back. You can connect it to an automatic gearbox that you shift manually. As a note, it wouldn't work well for a manual gearbox because since this engine doesn't speed up and slow down easily, it doesn't work as well for clutching and doing all that. So if you have a manually shifted automatic, it works a lot better. A torque converter theoretically could work as well, but in this circumstance, that was the easiest and best thing. The other thing is the general spatial consideration of it isn't bad. It's rather lightweight, and I don't remember the specs right now, but it's much lighter weight than like a small block Chevy or something like that. It's rather narrow. The biggest part is the front compressor section area. And it's fairly long. I mean, it's the length of a V12, so you need to have a healthy engine bay to put that in. Of course, you got your intake up here. And it worked out in terms of spatial considerations really well. In regard to a Batmobile, as it was portrayed in fiction, you guys remember it has the giant cone on the back for thrust where fire would be coming out. Of course, that was a movie a long time ago. It would be it's effectively impossible to make a Batmobile, as it was portrayed in fiction, be real, because if you have a giant turbo or engine in here, a turbine engine, that's going to direct thrust out of the back of the engine, then what about the cockpit in the middle? Okay, so it wouldn't work at all. In this circumstance, what I've done is direct the exhaust, because all the thrust, which is being directed internally to those blades to spin the gears and everything that eventually gets the wheels, that thrust and that heat has to go somewhere. So it does have exhaust. If you come over here a little closer, you can see, and I've got them covered with this insulative material because they get very hot coming out here and coming out the other side is there. And I can't remember how big around they are. Let me look here. They're about 6.5 to 7.5 inches diameter. And this is no ricer tailpipe action. That is actually the diameter you need for the thrust and heat that can come out of this. If it was to be smaller, you'd be upping your effectively compression there and creating much higher temperatures, and you're going to lose power and you're going to create much higher temperatures. You might melt something down. So that's actually what it needs. That is another reason why turbine engines don't really do that well in cars, because they make mass quantities of heat and gas and thrust coming out of it. Which generally you'd like to have shooting up away from people and things as best as that you can. I know that Jay Leno on his Y2K motorcycle that uses the Allison Rolls-Royce variant has those 2 big exhaust stacks. And on the Y2K bike, they actually inverted the motor and changed the oil pickup system for that bike with the thrust directing out the bottom. And yeah, if you did park it close enough to a bumper or something, you will start melting it, which is sort of fun. And the bike is completely absurd, and Leno loves it. And actually, I've met him, I've hung out with him in his garage once and checked that out, and he's exactly the same person in real life. I know that's a tangent. But anyway, so this one, so we got the big exhaust coming out the sides. I've got EGT, or exhaust gas temperature leads, going to both of them. That's highly important on a turbine engine in case something goes wrong in the startup phase or fueling, so you don't start melting it down internally. Turbine engines really started to be developed in World War II. The Germans got the leap on that in their first, I think, service aircraft, which is the Messerschmitt 262, which had 2 turbojet engines. So back then they were really hardcore working on developing the alloys and the materials to be able to make these engines, because before that we didn't have the material sciences to make something like this that can spin at that high of speeds as well as those high of temperatures to make it work. And actually I think there was a British guy that effectively invented it, but his commanders just thought it was impossible. They don't have the metallurgy, and I don't think he ever got credit for it, but which is an interesting thing to look up. So with regard to this, Let's just go over some details here from front to rear. That might make it easier. This is the oil cooler. Of course, it has oil, it has its own sump, and it's mechanically driven. This oil cooler, when it had been utilized on an aircraft or even a generator or something like that, would have been on the very bottom of it. And the reason being, when the exhaust is thrusting out so much like that, it would have had these extra, shall we say, cones or shrouding on the outside. And with the speeding of the gas coming out in either a helicopter or a generator, that would effectively draw a low pressure. And this was connected on the bottom, so cool air would come in through this and be drawn out with the low pressure being created by the thrust coming out. So that's kind of neat. That's really great engineering when you can utilize something, the exhaust gases, to actually do more work and bring in cool air for the oil cooler. Of course, in this circumstance, I had to direct the exhaust out of the vehicle. So this is up front, and there's an electric fan that helps it for the engine, for the the oil cooling. I have a pretty standard, right here, if you can see, racing type spin-on oil filter. Not much different than you put on a race car with a small block Chevy or something like that. As well as for a pressure lead here for oil pressure, and using high pressure lines with AN fitting. AN, if I'm not mistaken, stands for Army Navy, and the same AN fittings you can buy at JEGS or any racing aftermarket place are exactly the same kind of things that fit old aerospace and military stuff. So isn't that cool? It just works out from your racing type stuff. There's also a cooler down there, kind of more rudimentary one for the transmission. You're going to want that a little bit because transmission does a little extra work at times than it might in a reciprocating engine. And then if you also notice right here, this screen, which is front here and on the side, I actually modified the old inlet screen, made it bigger, and that's effectively the filter. I'm air quoting that. So all the air that goes in the turbine engine is from this. Naturally, in a ground setting with this, there's going to be a lot of dirt and whatnot. So if this vehicle was actually used off-road, or you were driving it and a lot of dust and stuff kicking up, more so than is reasonably normal, you would want to filter it better. But for as much as this particular vehicle is used, this does a good job of filtering things out that might chew up some very fast spinning blades. The motor, the engine, is mounted in here. If you want to come over, you might be able to see this better. Right here. So this is your big compressor side. The air comes in here, it spins out here. This is kind of like a giant centrifugal supercharger in a way, but it's part of the engine. And then these mounts right here, very nice mounts, very lightweight. They go in here to these 12-point fasteners. Originally would have been down at the bottom, but the beauty of this, since it's a circle and it's a radial in that circumstance, I was able to just take out the bolts and clock these mounts to be up high and meet right here to the node of the tubular space frame that I created. And then of course there's a bolt here, and then I have the correct durometer of energy absorption on both sides so that you can get rid of any vibrations, or if you have a little bit of torsion, it'll take it up, and that's worked really well. So the motor hangs in the front with those two mounts. In the rear, if I'm not mistaken, the transmission mounting plate, or the adapter plate, which is this big, looks like it's about 1.25 inches thick aluminum. It's been a while since I've done it. Those are actually mounted to the chassis back here. So it mounts rigidly, which is very similar to how racing small block Chevys are done on a lot of race cars or sprint cars, etc., where you have an engine plate on the front and the rear to mount. It's actually kind of the same way the small block Chevy actually mounts in the Genius Garage yellow Corvette racing car. So not a whole lot different going on there, just basic good engineering for aerospace and racing world. If you notice here on the billet aluminum plate of the engine back here, which is the adapter, we're going to get into that more detailed. I have this one rod, and that is just if there was more torque and whatnot, the thing would turn this way, so it's in, I believe it's in tension. Don't make me think too hard today. I got to go traveling. Anyway, that's basically a torque rod. I probably overkill, but it was easy and nice to do. Makes a lot of good engineering sense, and also there's a certain amount of float that can happen with the drivetrain. Okay, so let's go on to some other things. These big tubes here, actually, that's for cockpit air. So, you don't either fry in there, or if you happen to get any funny fumes, if something weird was going on with electrics or whatnot, you've got a cool air supply from the front of the car going there. The gold reflective material looks kind of like something you'd see on one of the Apollo missions. Spacecraft is basically the same kind of stuff. These are places where I wanted to insulate from any heat. In some ways overkill, but we're doing just fine and have never had any issues. The other aspect is the electric fan that I utilized to cool the engine oil cooler as well as the transmission oil cooler. It also doubles where any air that's not being directed to that is directed into the engine bay. So I have a constant flow of cool air into the engine bay, which goes beyond just what the intake is. And the point of that is that you don't have any stagnant hot air around your exhaust. It can flow out and around. And so then the hot exhaust from the the now warmed up air from the hot exhaust can come out these louvers, which when you move through, when the car is driving, creates a low pressure through the stainless steel screen, and hot air can vent out of here. As well as there are big channels, and you can pan back and see it too. If you notice, I'll come around. The big exhaust comes out right here. It's at a 45-degree angle and slightly upward to get it away from things on the ground. But there's also big channels in here, which effectively be some crash protection, believe it or not, that are open for air or any residual hot air to go out the back and vent sort of in the wheel wells and out the back. So it's actually, even though that it's a fictitious car and a custom build, I thought it through that far in terms of all of the airflow, and it's worked very well from the get-go. Those are the basics in terms of the logistics in getting it to just fit in here. So let's go into the basic of how the engine works, and then we'll come to the ancillary and all the fun little items. So as we saw up here in the front, this is the inlet screen. And you go to your centrifugal, your compression stage here, which is sort of like a big centrifugal supercharger, and I do mean a big one. So it's an intake here, and this section up here is called the gas generator. That's what compresses the air, puts it into two combustion chambers, and creates the thrust. The gas generator, if you guys will remember from a previous video I did on the operation of the cockpit, creates your thrust. This is what's creating the power, and it has its own tachometer made specifically just for this. It idles at just under 20,000 RPMs, and I believe the maximum RPM, if I remember correctly, it's been a while since I built this thing, is somewhere in the area of 40,000 RPMs. There are turbine engines that spin faster, but this one spins at that speed, which obviously is fantastic for a reciprocating engine. But there's no pistons going up and down and valves going up and down. It's just spinning. So in the nature of this, that works out much better. Things just have to be balanced beautifully with super high tolerance precision, because keep in mind, you've got little tiny metal blades spinning so insanely closely to a wall to have good compression. Kind of in a matter of speaking, the way a rotary engine has to make good compression with those seals as they're spinning. But these don't have seals, it's just really tight tolerance. So anyway, you have your gas generator here. And you'll notice this kind of section through here with these ancillary items driven off here. This is your gear section, okay? There are gears here that are mechanically always connected to the gas generator side. And they do a number of things. So when you first have to start this up, it utilizes this electric starter, which is 24 volts, to actually spin this thing up. Once you hit it in the area of 3,500 to 4,000 RPMs on this, then you can put in the fuel with the sparking. And if it fires and starts creating compression, it'll start spinning up. You turn this off at a point, the starter, and then it turns into a generator, because an electric motor, if it's doing the spinning, you're putting electricity in it to do work. But if it's being spun by something else, it'll create an output of electricity. Kind of neat, huh? So that's what's going on here, and it's gear driven and always connected to this. So it's either being a starter or it's being a generator. Now over here, you got your mechanical fuel pump. And you'll notice the inlet line here that goes to a filter and all the way back to the fuel tank or fuel cell, which is behind the cockpit. You can see that right here. That's the fuel filter and the line, of course. And then here's your mechanical fuel pump. This is a high pressure. I don't recall the PSIs we're talking about, but it's high, okay? If I'm not mistaken, like for instance on a diesel car engine, you know, the injection pressures can be, I don't know, 15, 20,000 PSIs. Like, it's dangerous. You work on a diesel engine like that and it sprays. That's such high PSI that if it hits you, if it spurts a leak or something, it can go right into your bloodstream and kill you. You need to think about that thing if you're working on something diesel. With this, you know, the fuel's very similar. Jet A fuel, which is what I run in this, is darn near the same thing as kerosene, just a little nicer. And they're very similar to diesel as well. So it's very high pressure, but you also have to have an electric fuel pump, which is backed by the fuel cell, which is lower pressure, to deliver the fuel to here so it doesn't cavitate. So it's always got a larger quantity of fuel moving at a lower pressure. And then this one, depending on the speed and depending on the throttle, which is right here and connected to it, it can actually put fuel in and meter fuel to the engine and to the combustion chamber based upon, one, how fast it's spinning and what it can take, as well as where your throttle setting is, and if you're utilizing a governor, where that is. So the mechanical fuel injection on this turbine engine is very similar to like an old Cosworth DFV Formula One engine, okay? They're driven, the mechanical fuel injection systems are driven off the engine mechanically, and then they do the similar sort of thing with throttles. Even sprint cars, you know, like old sprint cars, dirt track racing, mechanical fuel injection also works in much the same way. So just because this is a turbine engine, you guys all think it's magical because it's from aerospace and the military blowing stuff up, doesn't mean that those cool things are happening around the world in racing too. It's all the same kind of basic stuff. Now you get your throttle assembly going on here. This is a vacuum, like a collaboration port or a communication port over here, because there is a governor which relates to the output shaft. So if you're trying to overspeed your output shaft, the governor back here communicates via vacuum to your throttle and says, hey man, lay off so you don't blow this stuff up. So that's pretty neat. Also, and I gotta remember how this crap works. Oh boy, it's been a while. This goes on, this gives you your tachometer lead, and you can get information out of here with how fast it's spinning and whatnot. And I don't know, it required a brilliant stroke of whatever to figure out how to make it work with the old military manual and nobody telling me how to do this stuff back when. So here's your mechanical fuel pump, and then its output, I gotta find it here. There's I believe, there's a return line, and then there's hard lines. So if you can see this down here, it looks like a brake line on a car. It's much higher pressure fitting. It's not really to be flexible or much, because then it diverts itself down here. There's a solenoid here, right here, big kick-ass solenoid. Now that solenoid is connected to a toggle switch in the cockpit, which is either off, on, or neutral. So if you turn it to the off position and leave it in off, it's getting electricity to hold it there. But if it's at off and then you flip it to neutral, it automatically stays locked in off. And it also works that way with the fuel. So if it's at off, you go through the startup procedure and you want to flip the fuel on, which at the same time connects to the ignition, which we'll get into. If you want to flip the fuel on to the on position, you could move the switch back to neutral and it'll stay locked in the on position until you electronically tell it to go to off. It's kind of interesting that way. So you got a big solenoid that is your last mechanical ability to stop fuel from getting to the combustion chamber. If you want to look down in here, and maybe tough to see, this big old round guy here, and maybe sometime I'll take one of these off. You got a big compression, or you got a big V-clamp type fitting, which race guys will notice from exhaust system. It's a sort of overkill. And then here are your two fuel lines that go to the injectors. This is one of two combustion chambers. And then back here is your igniter, which is effectively just a big, just otherworldly insane spark plug. Now, the combustion chambers are these round areas, and on the inside of them, it's just not just completely open inside of there. The compression comes in, and there's something that's sort of like, it's like a Swiss cheese bell inside of there, and your injectors. Because what happens is when you're injecting the fuel in there, and you have the right compression and conditions are right, once it's done sparking, the flame, or the flame front, needs to stay lit. So if you ever heard old fighter pilots saying like, light, 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 you want it to like light it, right? Because then when you turn off the startup sequence, you've also turned off the igniters. And if the engine is in optimal conditions, it will stay lit. The fire will stay burning. And what you've done is you've created compression, a massive amount of compression of the air. It's also getting hot, going into your combustion chambers. And this is an older school variant because the combustion chamber's on the outside and then they have to go back in. Turbojet engines, when they evolved later, they didn't do that. They didn't go to the outside and then back in. What they did is they just made it so there were lots of compression stages all going in the same direction, like a modern turbojet engine. Because it's more efficient to make a lot more power. So if you ever go to like the Air Force Museum down by Wright Pat, National Museum of the Air Force, you'll see old engines and you can see the development of that. This sort of works in the older timey way. It's a little more compact, still works really well, but theoretically you could make more power if you could all keep everything happening in a line. So there's some good wisdom you can learn there. So anyway, the flame front stays, and once it's lit, if you've got everything optimally set up with the nature of the way you're injecting fuel and the mechanical fuel pump, it'll bring it up to that idle at just under 20,000 RPMs, and it'll stay there. Everything's communicating well. And then with the systems from the governor, it's not being oversped to your mechanical fuel pump, and you got a good flame, all your conditions are optimal. Then it really comes down to the throttle, which is right here. And this is the cable that pulls, that's literally just connected to the gas pedal in this custom car. And you can throttle it up. The thing about a turbine engine, and I say turbine, not just turbo shaft, that can be a turbojet engine, whatnot, they create almost all of their power at much higher RPM ranges. So if you're at idle, at 20,000 RPMs, you really need to be at like, 30+ thousand RPMs if you're going to be making a lot of power. So truthfully, in a circumstance with this, for a ground-based vehicle, if you're just sitting there idling and holding the brake, and you stick your foot on the throttle all the way, you're not going to go anywhere for a minute. So if you really want to take off, you need to be spooling up the engine, because it's literally just a giant turbo or supercharger. That's what it is. This is basically powered by a giant turbocharger that you're sticking fuel in. That's all it is. So it gives you new meanings to the phrase turbo lag, because that's all it is. But once it makes power, it makes a lot of power. That's why I've used funny analogies of it being like this otherworldly magical sailboat of power thrusted by the hand of God. Because it doesn't just hit you. You're managing thrust to drive the rear wheel. So you really have to be smart with some left foot braking and whatnot. And frankly, there are times when you're driving it, especially if you're driving it on the street, it's not ideal, okay? Now, as a note on that, some of you know of the race cars in the 60s that had turbine engines, turbo shaft engines that drive the rear wheels. Those are the Indy cars most notably. That was not a big deal for them, because once they're up to speed, they can just rock and roll for a long time at high speed, the same thing. That works great. They're really simple. And if it wasn't for, an O-ring in one of them, would have won the Indy 500. And of course they got banned, because I promise you all Indy cars to this day would be turbine powered if it wasn't for things that relate to fuel or just rules for the sake of rules. Because in the sense of oval racing, it makes all the sense in the world, as it would with boats or airplanes, where you're at a constant speed or pressure for long periods of time. And frankly, they're very fuel inefficient in this circumstance. It's another reason why they're not widely used in ground transportation and cars. So that's a big thing. But a car of great note was the Helmet Turbine Car. Now, it was a closed cockpit, Le Mans type endurance racer. Now, that car was actually really one of Bob McKee's design. It's a McKee Can-Am car underneath there, tube frame that had a full body. Now, there's a couple of real cars out there, I think, and a replica. And they're actually not using the original turbine engine. They have that Allison Rolls-Royce variant that's used in the Y2K motorcycle, as well as Tavares was thinking about putting in a Testarossa. The reason why that doesn't work well in a car, especially a road race car or a street car, and isn't appropriate for that car, is because, like I said, it takes a long time for it to make the thrust and make the power and then spool down. So it works well in Indy cars, airplanes, and boats, but not real well in road racing or street cars. So the way the original Helmet turbine engine worked well was it had a giant wastegate, okay? Giant wastegate. So effectively, the Helmet turbine car solved its problem by making thrust to come out of corners fast by running the gas generator full throttle all the time, or wherever it needs to be for fuel consumption. So if you run at full throttle all the time, you're saying, well, Casey, how do you slow down for a corner? Well, it was simple. That thrust is directed upon the driven blades and then eventually the planetary gears to drive the wheels, right, internally. But if you suddenly had a gate that could open up and direct the thrust out, then you would be putting none of that thrust toward the wheels. But you can keep the gas generator spooled up all the time. So if you close the wastegate, all of the thrust will be directly and immediately directed into the driven blades as well as to the wheels. So that's how the original Helmet turbine car came out of corners fast. It's just your fuel consumption was crazy like that. Now, that's not something you can reasonably or realistically easily do with an Allison Rolls-Royce 250 variant, which Tavares wants to do in his Testarossa. I think it's a bad idea. They did in the Y2K bike, couldn't do that. And frankly, this one doesn't do that either. But that's how they did it. And it's absurd and makes no sense for fuel consumption and all, but that's how the Helmet turbine car actually came out of corners well. And also, by the way, I'm really self-conscious right now, because even though this is a fake gun, I've got a machine gun muzzle pointed right at my junk, which as a safe shooter, that's really weirded me out. I really just don't like that pointing at my pelvis. Okay, I'm gonna move. So anyway, you guys, that's really how it works. It's an exciting thing to be part of. Turbine engines are hard to find. You really want one that can be throttled if you're going to use one in some sort of fun build. Even though this is a turbo shaft engine and creates its thrust to drive a shaft and output, The other thing that's neat, you can take an engine like this and take it apart sometimes. Like this one, if I took it apart in stages in the middle and removed all the driven blades and the planetary gear sets and all, I could run the gas generator alone and just make thrust. So then if I built a nozzle out of in-canal or an appropriate alloy, or even put an afterburner, I could turn this into a turbojet engine that's throttled. Now, it's not going to be the best turbojet engine in the world, but it's going to make thrust. And I've seen people do that on everything from crazy, like, I don't know, you want to make your outhouse jet-powered, hooray. I mean, like whatever, you can do that. And that's fun and that's exciting. That's why I like to have turbine engines around to teach people, and I want to do this video because it gives you guys all an opportunity to see how this works, because otherwise it's a lot of mystery. It's old surplus engines that people don't really get the opportunity to do something with. As a note, this box here is effectively your igniter box. And there's 2 igniters, 1 for each combustion chamber. If you want to walk around, you actually might be able to see it pretty well. The original igniter box on this engine was eventually prone to failure, and it did in fact fail. This one now has 1 igniter box for each one of the igniters. This is the big lead, you know, with the typical military spec connectors that's going to the combustion chamber. Works really well. These igniters are so powerful, you can put it underwater, and it's just like little explosions every time. Like, even underwater, it's amazing. So the last thing, which I'll give you guys a tip, you know, the output shaft on this particular engine was great because its spec was for 0 to 6,000 RPMs output shaft, which is like every reciprocating engine in the world now, and it spun the same direction. So it's perfect, but it still required some engineering to do. So you have an adapter plate, and I have this big thick one right here, and machined it so obviously it could bolt onto the engine's output flange. And then in the middle had a big support bearings, high-speed bearings, that were sealed. And I had to draw a shaft that was a male shaft that was splined to go into the female splines of the output of the planetary gear set of the motor. So the male shaft goes in there like that and connects. Then it has a journal surface so it could ride in the high-speed bearings that are in this. And then what I did to make it work well, I just had the output flange be the same as a small block Chevy. Small block Chevys are probably the most available engines to build in the aftermarket, so it made a lot of sense. Then I can just adapt it to a flex plate or a clutch or a flywheel or whatever I need to best utilize to make it work with the transmission. Transmission in this is a 4-speed General Motors derivative automatic, which I modified to be manual shifting only. So basically, we've got an RPM for the gas generator to know how much thrust we're making, a tachometer that is, and we have a tachometer for the output shaft speed. So, you know, with my right foot, I make thrust. I see what that's doing based upon its RPM and what my right foot is thinking. And then I utilize the tachometer for the output shaft to know what gear I'm in, and is it time to upshift so I don't overspeed, or to be a little more chill, or is it time to downshift to make more torque. And that's how that works. And it's basic adapting of other engines. It's really no different than if I wanted to take a Porsche transaxle and put an LS up to it, like is done in the kit car world. It's just that this is a turboshaft engine with much different needs and much different logistics and you know, different positives and negatives, drawbacks, etc. But in this circumstance of making a fictitious car more real, it was absolutely perfect. I was really happy with the way it executed. I wouldn't have built it if it wasn't going to be that way. And I obviously want to share that with you guys because I think it's a great learning lesson. And maybe some of you young people will utilize this as a stepping stone to do something amazing in the future. So that's about it. I think I'm about sick of talking for right now. I can't think of anything else, but you guys really need to, I would appreciate it actually if you liked and commented. That's always fun. And I'll do my best to get back to you in the comments, but please subscribe and also share it. I will be coming back. We will drive it. And I'm gonna roast some marshmallows or see if I can cook a steak on the exhaust because it's really hot and that will be fun. And that's what the internet likes, and that's probably what you need to grow a channel. Anyway, see you guys next time.